If you love space and want to see more mind-blowing science videos, make sure to like this video, subscribe to the channel, and turn on the notification bell so you never miss an upload. And before we dive in, if you have ideas for future videos, drop them in the comments, because I read them and they really help shape what comes next. Now imagine two objects so dense that a teaspoon of their material would weigh more than a mountain, spiraling toward each other at half the speed of light, bending space itself, and finally colliding in a cosmic explosion that releases more energy than all the stars in the universe combined for a brief moment. That is not science fiction. That is what happens when black holes collide. But how do they actually do it? What does the process look like? And how do we even know what happens if black holes emit no light? To understand black hole collisions, we first need to understand what a black hole really is. A black hole forms when a massive star collapses under its own gravity at the end of its life. The core compresses so intensely that gravity overwhelms every other force, creating a region where escape velocity exceeds the speed of light. The boundary around this region is called the event horizon, and once anything crosses it, not even light can escape. Despite their reputation as cosmic vacuum cleaners, black holes do not randomly wander around swallowing everything. They follow the same gravitational rules as any other object with mass. If our Sun were replaced by a black hole with the same mass, Earth would continue orbiting almost exactly the same way. The difference is that black holes can be extremely compact, and when two of them get close, gravity becomes incredibly violent. Most black hole collisions begin long before the actual merger. They start with two massive stars that were born together in a binary system, orbiting each other for millions of years. Each star eventually collapses into its own black hole, leaving behind two invisible objects locked in orbit. Over time, something remarkable happens. According to the theory of general relativity developed by Albert Einstein, accelerating masses should create ripples in spacetime called gravitational waves. These waves carry energy away from the system. As energy is lost, the black holes spiral closer together in a slow cosmic dance that can last billions of years. At first, the orbit shrinks very gradually, but as the distance decreases, the process accelerates dramatically. Picture two whirlpools forming in a river and spiraling toward each other, except instead of water, they are twisting the fabric of space itself. As the black holes approach, they begin orbiting faster and faster, sometimes hundreds of times per second. This stage is called the inspiral phase. During inspiral, gravitational waves grow stronger and higher in frequency, like the rising pitch of a siren. Eventually, the black holes are moving so fast that they distort each other's shapes through tidal forces, even though they are not solid objects in the usual sense. Space around them becomes a chaotic storm of extreme gravity. Then comes the moment of merger. The two event horizons touch and combine into one larger horizon. Contrary to what people sometimes imagine, there is no explosion in the traditional sense because explosions involve matter and light. Instead, there is a sudden and violent reconfiguration of spacetime itself. A tremendous burst of gravitational waves radiates outward at the speed of light. For a brief fraction of a second, the power released can exceed the combined luminosity of every star in the observable universe. Yet no flash of visible light may occur, meaning that from a distance, the event would appear completely dark unless you had a way to detect gravitational waves. After the merger, the newly formed black hole is not immediately stable. It vibrates and oscillates, like a struck bell ringing in space. Scientists call this stage the ring-down phase. Gravitational waves continue to radiate as the black hole settles into a final shape determined only by its mass, spin, and electric charge. This simplicity is sometimes summarized by the phrase, "black holes have no hair," meaning they lose all complex features during formation and merger. For decades, black hole collisions were purely theoretical because gravitational waves were too weak to detect with existing technology. That changed in 2015 when scientists working with the LIGO Scientific Collaboration made the first direct detection of gravitational waves from a black hole merger. The signal, known as GW150914, came from two black holes about 1.3 billion light-years away. When the data was converted into sound, it produced a short chirp lasting less than a second, representing the final moments of inspiral and merger. This discovery confirmed a major prediction of general relativity and opened an entirely new way of observing the universe. Soon after, additional detections were made by LIGO, along with its European partner, the Virgo collaboration. Scientists realized that black hole mergers are not rare events. They happen frequently across the cosmos. Some involve stellar mass black holes, only a few times heavier than the Sun, while others may involve intermediate or even supermassive black holes containing millions or billions of solar masses. When galaxies collide, their central supermassive black holes are expected to eventually merge as well, producing gravitational waves so powerful that future detectors in space may observe them across enormous cosmic distances. One of the fascinating aspects of black hole collisions is that they challenge our intuition about space and time. Near a black hole, time itself slows down relative to distant observers due to gravitational time dilation. As two black holes merge, these effects become extreme. From far away, the process appears to stretch in time as signals struggle to escape intense gravity. Yet locally, the merger happens quickly. Physics near the event horizon operates under conditions we cannot replicate anywhere else, making black hole collisions natural laboratories for testing the limits of our understanding. Another surprising phenomenon is the possibility of recoil, sometimes called a black hole kick. If two black holes merge in an asymmetric way, meaning their masses or spins differ significantly, the gravitational waves emitted can carry momentum in a preferred direction. This causes the newly formed black hole to recoil, sometimes at speeds of thousands of kilometers per second. In extreme cases, the black hole could even be ejected from its host galaxy, wandering through intergalactic space alone. Astronomers have found candidate evidence suggesting that such events might occur. You might wonder what would happen if you were close to a black hole merger. The answer depends on distance. If you were millions of kilometers away, tidal forces could stretch. Gravitational waves passing through your body would technically distort you, but the effect would be tiny unless you were extremely close to the source. Fortunately, black hole mergers we detect are usually billions of light years away, so they pose no danger to Earth. Scientists are also interested in whether black hole mergers produce light under certain conditions. If the black holes are surrounded by gas, dust, or magnetic fields, the violent motion could heat nearby matter and generate electromagnetic radiation. Some observations hint that light flashes might accompany certain mergers, though confirming this remains challenging. Missions and observatories supported by organizations like NASA are actively searching for such multi-messenger signals, combining gravitational waves with traditional astronomy to build a more complete picture. The mathematics behind black hole collisions is incredibly complex. Solving Einstein's equations for two merging black holes requires massive supercomputers and sophisticated numerical simulations. These simulations help scientists predict the gravitational wave patterns expected from different scenarios. When detectors observe a real signal, researchers compare it with thousands of simulated templates to determine properties like mass, spin, and distance. In this way, gravitational wave astronomy acts almost like cosmic forensics, reconstructing events that happened billions of years ago. There are still many mysteries. We do not yet fully understand how some black holes grow so large or how often intermediate mass black holes form. Some theories suggest primordial black holes may have formed shortly after the Big Bang and could also merge today. Others speculate about exotic possibilities, such as wormholes mimicking black hole signals, though current evidence strongly supports standard black hole physics. Each new detection helps refine our models and sometimes reveals unexpected surprises. Black hole collisions also teach us about the fate of the universe. Gravitational waves carry information about cosmic expansion and the distribution of massive objects across space. By measuring many events, scientists can estimate how frequently black holes merge and how galaxies evolve over time. Future detectors in space, like planned gravitational wave observatories with arms millions of kilometers long, could detect mergers involving supermassive black holes and even signals from the early universe itself. Perhaps the most awe-inspiring aspect is that these events connect us directly to the fundamental structure of reality. When black holes collide, space-time is not just a background stage where physics happens. It becomes the actor itself, stretching, compressing, and ringing like a drum. The universe is not silent. It is full of vibrations, and we have only recently learned how to listen. As technology improves, we may eventually detect hundreds or thousands of black hole mergers each year. Some could challenge our theories, revealing new physics beyond general relativity. Others might confirm ideas about quantum gravity or the behavior of matter under extreme conditions. Every collision is a message traveling across billions of years to reach our detectors, telling a story about stars that lived and died long before Earth even formed. And when you think about it, there is something poetic about two invisible objects colliding in total darkness. Yet producing signals powerful enough to be measured across the universe, it reminds us that reality is often stranger and more beautiful than imagination. We are living in a time when humanity can observe the universe not only with light, but with gravity itself, opening a new era of discovery that future generations will build upon. I would love to hear your thoughts, so let me know in the comments what you find most fascinating about black holes or what questions you still have. Your comments really help guide future videos and discussions. And if you enjoyed this journey, don't forget to like the video, subscribe to the channel, and turn on the notification bell so you never miss the next exploration into the universe. Thanks for watching, and see you next time.